Please label these notes Antiderivatives 3 notes, U-Substitution, and write today's date. By the end of this lecture, you should be able to use U-Substitution, which is sort of the equivalent of the chain rule, to find antiderivatives. So let's start off with our first example problem. Let's say that we're trying to find the antiderivative of 3x plus 6 to the 4th power dx. Now, we saw over in Antiderivatives 2 notes that if we had something like this, we could just expand it out and then take the derivative using the power rule. However, this is to the 4th power, so we would have to do the generic rectangle several times in order to get this all the way expanded. That would kind of be a pain. And so what we're looking at here is a faster way to do that. To use U-Substitution, the first thing we're going to do is look for our box functions from the derivatives unit. But there's going to be one change. We're still going to have powers, so that's box to the nth. We're still going to have trig functions, so that's functions like sine of something or cosine of something or whatever. We're still going to have exponential functions, so that's like e to the power of something. But instead of having logarithmic functions, so this was ln of box, instead of doing that, we're going to look for 1 over something that we can put in the box. So right here we've got powers, so we can put our box around there. And now what we want for doing the U-Substitution is we want whatever is in the box to exactly match whatever variable we have here. So rather than the chain rule where we were taking things out of the box, here we're condensing down the whatever's in the box until it exactly matches whatever's after the d. So let's take a couple notes over here on that, and then we're going to go back up. We can only take the antiderivative if what is in the box exactly matches what's after the d. And basically what's here is always going to be a variable. It might be x, it might be t, it might be theta, whatever, but it's always going to be a single variable. And it also has to be the case that there are no other variables. So if we've got a dx over here, we'd better not have a t or something hanging out in the equation. Unlike the chain rule, where we take things out of the box, for U-Substitution, we're condensing what's in the box. And basically, U-Substitution is another form of rewriting. We want to make it so that we have one of the rules that we've memorized, and now we're just doing some more creative stuff to make this into something that we know what the antiderivative is. Because, for example, right here, we know what the antiderivative of x to the 4th would be. We just add 1 to the exponent divided by the new exponent. But this isn't just plain old x to the 4th. It's something else. and we have to make that something else look exactly like our rule. So our rule is that the antiderivative of x to the n is x to the n plus 1 over n plus 1. So we need to have a single variable here to the fourth instead of this function. So what I'm going to do is I'm just going to create a new variable. It's typically called u for whatever reason. And I'm going to let that u equal whatever was in my box. So 3x plus 6. And then what I'm going to do is I'm going to do a rewrite right here where I'm just going to take out that 3x plus 6 and I'm going to put u in instead. So now this is in the form that we're familiar with, but these variables don't match. And remember, we can only take the antiderivative if what's in this box here exactly matches what's after the d. So somehow we have to change this from a dx to a du. These not matching is not okay. That says not okay. So what we're going to do is we're going to come over here to this u, and we're going to say, alrighty, we can get a dx in here if we do the derivative of this function u with respect to x. So all I'm going to do is I'm going to take the derivative with respect to x of 3x plus 6. We know how to do that, so we just look here. The derivative of 3x with respect to x is 3. And now what I'm looking at here is that here I've got a du, and I want this u in order to match that u. And I've got a dx, which is what's in my equation right here. And so now we're going to do something kind of funky with this. Because in the past we've looked at this notation and said that this just means the derivative of u with respect to x. It's sort of this whole unit all on its own. And what we're going to do now is we're going to look at this as actually two separate pieces. So if I want to get dx by itself so that I can substitute in for this, I'm just going to multiply both sides by dx. And then divide both sides by 3. Because now what I have is I have this dx here, which can be substituted in for this dx up there. So I'm going to do that. Dx equals du over 3. And now I'm in a situation where my box and what's after the d are exactly the same. That's exactly the same variable. And now I'm in a position where I'm allowed to take the antiderivative. A lot of people have questions about what this 3 is. This 3 is really just the same thing as a 1/3. So this is the antiderivative of u to the 4th times 1/3 du. Remember our constant multiple rule. This is just a number multiplied by everything else, so it can come out as just along for the ride. And I'm going to have 1/3 times the antiderivative of u to the 4th, excuse me, du. Now that this is just a single variable, I can use my power rule. I'm going to add 1 to the exponent, so that's u to the 5th, divide by the new exponent, plus c. This and this go away. Now at this point, I'm done taking the antiderivative, but when I started off I didn't have a u, I had an x. And I want to make sure that I end with the same variables that I started with. So one of the things that we see here is we see that u equals 3x plus 6. So I can just take this 3x plus 6 and stick it right back in there. So this came out to be 3x plus 6 equals u, and then that goes back in down here. So I can multiply that together. That's 3x plus 6 over 15 plus c. And there's my antiderivative. so that's to the 5th. That's to the 5th power. There, that works better. The idea behind this is that U-Substitution puts in place the pieces that would be undone by the chain rule. So it's very important to always check our work with U-Substitution. I'm going to go ahead and take the derivative of this and see if I end up back with what I started with. So let's check it. We're going to do the derivative with respect to x. 3x plus 6 to the 5th power over 15 plus c. Plus c is going to drop out because its derivative is 0. So this is the same as 1/15th, and then we're just going to do the derivative of this piece. So we bring down the 5 and subtract 1 from the exponent. And then, because of the chain rule, we do the derivative of what's inside. Just like that. So this is 1/15th times 5 times 3x plus 6 to the 4th times 3, because that's the derivative of 3x. 5 times 3 is 15. That cancels out with that 15 there. And we get 3x plus 6 to the 4th, which is exactly what we started off with. Now we're just going to do a bunch of examples. Really with this, you just need a bunch of practice. So let's start off by taking the antiderivative of 7t plus 8 to the 3rd power, and that's with respect to t. Now these variables currently match, but we have a box function right here that says power to the 3rd power. So we need this and this to match exactly. So I'm going to take what's in the box and I'm going to let that be u. And so I can substitute in that u to the 3rd. But I need to make this dt be a du instead. So I'm going to take the derivative of u with respect to t over here. So that's just the derivative with respect to t of 7t plus 8. That's just 7, and the derivative of 8 is 0, so it goes away. Now I want to get dt by itself, so I can substitute here. So I'm going to multiply both sides by dt. du equals 7 times dt. Divide both sides by 7. And now I'm going to go and I'm going to take that and I'm going to put it back in over here. So du over 7. There are a couple of things you need to become really fluent in, really automatic in. Getting from here to here should be really fast. You can also just see that these are going to switch. Also, when you see du over 7, that should automatically register as 1/7. That 7 needs to stay in the denominator, u to the 3rd du. Now we can use that power rule just like we did over here. Increase the exponent by 1, divide by the new exponent, plus c. So that's u to the 4th over 28 plus c. And now we started with t's, so we need to end with t's. So we're going to take this u and we're going to put it right back in down there. 7t plus 8 to the 4th over 28 plus c. Now we're going to come back over here and do our check step. So the derivative with respect to t of 7t plus 8 to the 4th over 28 plus c. We've got 1/28. We're going to bring down that 4 and subtract 1 from the exponent. And we're going to do the derivative of what's inside. It's 1/28 times 4 times 7t plus 8 to the 3rd times 7. 7 times 4 is 28, that cancels out there, and we end up back with what we started off with, which is good. Let's look at a problem where the U-substitution acts in a little bit of a different way. So let's say we're finding the antiderivative of x to the third and then times 2x squared. 2x cubed minus 4 to the fifth. This is dx. So again, we're looking for our box functions. Now we see that there are two here. This one right here is a power rule, or has an exponent, so we could put a box around it, but it already matches with the dx, so there's no need to do that. Here, this to the fifth power doesn't match with the x, so let's let that be our u. And I'm about to put that to the fifth power, but I shouldn't do that because the fifth is not there in the box. So when I do this substitution, I still have this x squared lurking around. This is now u to the fifth, and I'm about to substitute for that. Notice right now we have two variables here. We cannot take the antiderivative until one of these variables is gone. However, once we do this U-substitution, we should see one of these go away. That's kind of the point of the U-substitution. So the derivative of u with respect to x, we bring down the exponent, so it's 6x squared. That derivative is 0. Now I want to get dx by itself, so I multiply both sides by dx. I divide both sides by 6x squared. You should be able to do it really quickly like that. If you're not real comfortable with it, here's how I did that. I started off with du dx equals 6x squared. I multiplied both sides by dx. du equals 6x squared dx. Divided both sides by 6x squared. And that's where I ended up with this. Now this comes over and pops right back in there. So this is du over 6x squared. So all of these are in the numerator, this is in the denominator. So that x squared and that x squared cancel out. And now all I have is 1/6 times the antiderivative of u to the fifth du. And this I can take the antiderivative of. Notice when I'm bringing this number outside of the antiderivative sign, I can only do this with numbers. No variables are allowed to just sort of wander out, but numbers are, because what we're using is that constant multiple rule right here, but we can only do this if c is a constant number. Variables need not apply. So the 1/6 is along for the ride. We increase the exponent by 1, divide by the new exponent plus c, and then we got to make sure that we have the same variables that we started with, so the u goes back in here. 6 times 6 is 36. 2x cubed minus 4 to the 6th power plus c. Always go back and check your work. Derivative of 1/36 times 2x cubed minus 4 to the 6th power plus c. We bring down that 6. The 1/36 is along for the ride. Subtract 1 from the exponent, multiply by the derivative of 2x cubed minus 4. So we have 1/36 times 6, 2x cubed minus 4 to the 5th, and then times 6x squared. 6 times 6 is 36, cancels out right there. We have that x squared left, just like we did originally. Here's another example. Let's say we're trying to take the antiderivative of the cosine of x times e to the sine of x, and that's with respect to x. So we see a box function here, but all that's inside it is x, so there's no need for it. E to the something is a box function, and there's a sine x there instead of an x, so that's a good candidate for our u. So let's set u equal sine of x. Derivative of u with respect to x is cosine of x. Multiply both sides by dx, divide both sides by cosine of x. Now this comes back here. And lo and behold, these cancel out. If they didn't cancel out and there was still an x there, we would have a major problem. So it's a good thing that they cancel out. Now we just have to remember the rule. The antiderivative of e to the x is just e to the x. So the antiderivative of e to the u is just e to the u plus c. Put our u back in. When we check our work, the derivative of e to the something is just e to the something times the derivative of that thing. Which is right what we started off with. Let's do a similar example except with fractions because they end up looking slightly different. Let's say we're just taking the antiderivative of e to the x over 3. Here we see same box function right there. These need to be the same. So our u equals x to the third, which is the same as 1/3 times x. So du dx, when we take that derivative, is just 1/3. Now we need to get dx by itself, so we'll multiply both sides by dx. Notice this fraction here. This is the same as dividing by 3, so to undo this, we can think of it as dividing by 1/3 or simply as multiplying by 3. If you're ever uncertain, you can always work this all the way out. So we have 3 du equals dx. This goes back in here. So we have the antiderivative of e to the u, and then 3 du equals dx. This 3 is still using the constant multiple rule, so it can just chill. We're going to take the antiderivative of e to the u du, same as we did on this one up here. So the 3's along for the ride. We have e to the u plus c. Put our u back in. And there's our answer. When we take our derivative, the 3's along for the ride. Derivative of e to the something is just e to the something times the derivative of that something. This is the same as the derivative of 1/3 x, so our derivative is going to be something that cancels out right there, and we end up back where we started. The final example before our check for understanding is going to involve the new box function that we have, or rather the natural log, or in this situation. Now, we could rewrite this as 1 times 6t plus 7 to the negative first power. But remember what we saw in derivatives, antiderivatives 2, which was here, that the antiderivative of 1 over x doesn't work out. The antiderivative of 1 over x is just the natural log of whatever that thing is. So here, we've introduced a new box function just for antiderivatives. So you want to look for this pattern, 1 over something, and that something, that's our box. That's what exactly needs to match. So here u is going to be 6t plus 7. du dt is just 6. So du over 6 equals dt. Stick it right in there. And so what we have is we have the natural log of 1 over u, and then du over 6. That over 6 is a 1/6 power, so 1/6 times the antiderivative of 1 over u du. This is the one we just have to know from our rule. The antiderivative of 1 over something is the natural log of that, plus c. Now we put our u back in. And there we go. This is an incredibly important rule to memorize. The antiderivative of 1 over u is natural log of u, because when it comes time to do our check, if you got it wrong going this way, chances are you'll get it wrong going this way too. And then you just end up making the same mistake twice, basically. So we've got 1/6 along for the ride. The derivative of natural log is 1 over whatever it is. And then we have to multiply it by the derivative of whatever was inside the natural log. So we have 1/6 times 1 over 6t plus 7. Derivative of 6t is just 6. And there we go. We're back where we started. Let's have you do a check for understanding problem now. Let's do the antiderivative of x cubed times the square root of 5x to the 4th plus 7 with respect to x. Don't forget to rewrite before you do anything. Try that one on your own. Let's restart the video when you're ready. Pause the video now. Okay, before we do anything else, we're going to rewrite this. This is 5x to the 4th plus 7 to the 1/2 power with respect to x. We see that we've got a box function right here. There's also one here, but this already matches, so we don't need to worry about it. So let's let u equal 5x to the 4th plus 7. Derivative of u with respect to x, bring down the 4 times 5, that's 20x to the 3rd. So du over 20x to the 3rd equals dx, which goes right in there. So we've got the antiderivative of x to the 3rd, u to the 1/2, times du over 20x to the 3rd. These x's cancel out. That 1/20th can come out. U to the 1/2 du. Now we're going to add 1 to the exponent, so make sure you don't get confused with the way that we do things with derivatives. The 1/20th is along for the ride. We add 1 to the exponent, so 1/2 plus 2/2 is 3/2. Divide by the new exponent and add c. Dividing by a fraction is the same as multiplying by a reciprocal. And this 2 and that 20 cancel out, so this is 1/10. 10 times 3 is 30, so it's 1/30th. We're going to put our u back in here. 5x to the 4th plus 7 to the 3/2 plus c. Now let's go and take our derivative. And when we take our derivative, we end up back where we started. This concludes Antiderivatives 3 notes.